Hi, good afternoon everybody, and thank you for taking the time out to attend our talk. My name is Anahita, and I'm a senior software engineer with Intel. I'm joined here by my colleague, Karthik Vadla, who will be speaking in the second half of this presentation. And what we're going to be talking about today is a predictive analytics workflow on DICOM images using Spark. DICOM is a format commonly used for MRI and CT images, and that's what we're going to be talking about today. So quick slide on who we are. We're from the Intel Nirvana team. The group that we belong to is the AI products group. Like you can see, Intel has a whole stack of products, frameworks, toolkits that it works on in the field of AI. Right at the top, you can see Intel does a lot of stuff with experiences. What I mean by that is drones, autonomous driving, end-to-end solutions. Also toolkits like the Intel DL training deployment, the Nirvana DL entire stack, which deals with the cloud and lower level ngraph and neon APIs. Frameworks like Spark. Intel's one of the lead contributors to Spark, where its performance is concerned. A lot of work goes into implementing algorithms for MLlib and also tuning them for Intel architectures, and also BigDL, that is Intel's deep learning on Spark. In addition to that, there are a lot of libraries like Intel's distribution of Python, Intel DAL that provide further optimizations, and then, of course, there's the hardware. Okay, so quick agenda slide, what we're going to be talking about today. I'm going to be introducing the use case. I'll walk you through some of the challenges involved in the use case and how we've overcome it. To get to a solution, we kind of need to understand what our data is. So we'll introduce you to the data that we're going to be talking about over here. When we say deriving insights, what exactly do we mean by that? So we'll talk about some of the questions we try to answer. What is machine learning and how it can help answer some of the insights. The tools that we're going to use and how Spark makes a very healthy environment to bring all of these tools together into an ecosystem. And we'll walk through the library that we worked on, that's Spark TK, that's Spark Toolkit, and followed by a demo, and also some contributions to the Spark TensorFlow ecosystem and performance metrics. Okay, so we have a vast amount of medical image data available with healthcare institutions and hospitals. Think of this each time that somebody goes in to get an MRI or a CT scan or any kind of image generated, there is an image with the hospital, right? And there's also not just the image data, but there's a ton of metadata that accompanies this image. By that, I mean a ton of things. I mean patient information, for example, your name, age, date of birth, your health stats, your blood sugar level, your cholesterol levels, and more detailed numbers. The status of the condition, whether you have a tumor or not, whether you have a broken bone or not, whether you have some abnormality or not. The method of image capture, maybe you were captured by a Siemens device or a GE device, or maybe it was a person who captured it, or it was automated, so a robot captured the image for you, and various other parameters that I'll talk about. And time to events. Like if you're part of a study, you might periodically come in to get these images and these metrics calculated. So maybe 1 month into a study, 2 months into a study, or maybe when you were diagnosed with the condition. So the main idea over here is to create a distributed technology needed to efficiently store, because we have to store it in a format that's understandable, scan, and analyze data in healthcare. So obviously doing this wasn't very straightforward. Some of the challenges that we faced are listed here. Getting data for experimentation is hard. So as an industry, when we are trying to find these solutions, we don't really have all of this patient data. So getting access to it is hard for security reasons and obviously privacy. Combining data from multiple public sources for simulation is another challenge, because you might get some DICOM images, say, or MRI images on Kaggle, but you might not get the corresponding patient-related information. So how do you create an environment where you can build a system without actual real-world data? Multiple tools exist. For example, you might need image processing libraries to run filters, to run dimensionality reduction. So that's maybe one suite of tools. Then you might have visualization tools. That is, you want to open up the image and see what it looks like. So you have your visualization tools coming in. Then if you have big data, because each of these images can be massively sized and accompanying them is a ton of metadata, you need to have a distributed system that can do it for you. And then, of course, the machine learning part comes in, where if you want to run your classifiers or regressors, unless you're implementing all of these from scratch, you need to be able to bring all of these components together. And then if you have multiple components, you need to make sure they're compatible with each other. So one format understands the other, so on and so forth. So our main challenge over here, or our main driver over here, was how do we make machine learning easy to use, overcoming these challenges. So I'll just introduce our data first. Like the talk suggested, this is DICOM. DICOM stands for Digital Imaging and Communications in Medicine. It's a standard format that is used to store, exchange, and transmit data, medical data specifically. It has its standards for quite a few imaging modalities like radiography, ultrasonography, CT scans, MRIs, radiation therapy. It's not just an image storage format, but it also has protocols for visualization, compression, and image presentation. So that was the image data that we had. Then comes the metadata. Metadata, like the name suggests, is data that accompanies any kind of data. So we divided this into 3 types of components here. Image-related metadata talks about the storage, maybe it's compressed or uncompressed, the date at which it was taken. Certain DICOM images come with certain parts of the image flagged out, so maybe some coordinates telling you which part of the image was flagged or which had the tumor or which had an abnormality, depending upon the use case. That's image data, so pertaining to the image. Then comes the patient metadata that's related to a patient, so your vital stats, your name, age, height, date of birth, medical history. I haven't broken down medical history, but you can imagine it could mean a whole lot of things depending upon what condition you're going in for. And then comes the device-related metadata. So like I said previously, it could be manufacturer information, it could be the operator who captured it, it could be method of capture, the time of capture, and so on. Okay. So what are some of the insights that we can derive with this? So can we develop smart filtering techniques based on image metadata? So I have all of this information about the image. Can I do some sort of a search to maybe say I want to see only those images of females between 35 to 40 who've probably been diagnosed with breast cancer? Kind of like doing a Control F or a Command F on images, right? Instead of doing it just on text to be able to come up with the images that you really only want to see. Or can we conclude and predict certain conditions based on patient metadata? So patient metadata, again, is patient health records or cholesterol numbers, sugar numbers. So maybe run sort of some analytics that can tell me that maybe men in this age category are likely to have a risk, or maybe they're likely to have a symptom, or so on and so forth. Can we classify image capture techniques and suggest improvements based on device metadata? So maybe some devices were not functioning too well, so we realized some images were not really giving us the good clarity that we needed. And maybe can we have a model or an algorithm that can study this and understand what is it that's causing deterioration in image quality? Can we combine image and patient metadata to conclude and predict things? This is fairly important because right up till now, we spoke about handling image data separately, and we spoke about handling patient metadata, that is your health record, separately. So can we combine the two? Maybe if we can make some sort of analysis that people with high cholesterol in this to this age group or this to this blood sugar level look like they have this tumor or look like they have this condition as reflected in their image data. So that's fairly interesting because we're able to now combine 2 very different data sources, that's image and numerical values. And can analytics help automate or improve image capture techniques? Like I said previously as well, maybe some devices are not capturing images too well, or maybe some operator is not doing the best job he or she could have done to capture that image because of which the quality was compromised. So can we have and improve these techniques? Or maybe automate it so that a robot can do it better than us? Okay, so this is where machine learning comes in. I'm going to try to talk about some of the solutions on a high level based on the questions that I just spoke about in the previous slide. So when it comes to patient data, you can do a ton of things. You can train certain classifier models on patient data to predict the presence of a condition. Classifiers basically classify or label their data into different categories depending upon the categories you fed it during training. So some of the common ones used, or you can try over here, are logistic regression, random forest, naive Bayes. Sometimes it's not just good enough to tell you if it's class 1 or class 2. Sometimes you want to predict the probability of you belonging to certain classes. So maybe you want to understand some sort of, not a discrete value. So a linear regression or a random forest as a regressor could be very useful in this case. Sometimes you might also want to understand the time to failure or time to an event. That's when survival analysis model algorithms come in. So you're predicting not just if it's a yes or a no, what is the time for something happening, or comparing risk of populations. The accelerated failure time model is an algorithm already in Spark, and the Cox proportional hazards model is something our team has implemented. So it's a distributed implementation that you could use to kind of maybe compare, say, the proportion of men to women getting a particular condition or a failure or an event. Okay, so that was machine learning with patient data. When it comes to image data, what can you do? You can compute the eigen decomposition of an image to reduce the space of the image. You can compute the covariance matrix, because sometimes the covariance matrix gives you more information than the image by itself. These can also be independently used as pre-processing steps that you could then probably send to a deep learning algorithm or build stuff over it. You can also compute the principal component analysis of the image pixel data. PCA, like you're familiar, is a dimensionality reduction technique. So you're kind of reducing your search space to go into just relevant features, it kind of removes some of the noise. So like I said, these can be used as standalone techniques or feature engineering. And the third type of data, what machine learning can do for your device data. It can predict trends in image capture techniques. Again, your classifier regressor can be used here. It can not just predict trends, but also device time to failure. The same proportional hazards model and the AFT that I mentioned can not just be used to predict failure to a person, but also the failure of a device. So if we know that this equipment is likely to fail in 3 months, you can have a backup ready, and this can be information a healthcare institute can find really useful. And also maybe recommendations, like using the collaborative filtering algorithm to maybe say how to capture the device information better or how the image could be captured better. So to do this, we have a ton of tools available in the ecosystem today. So there's DICOM. It's a single-threaded Python package working with DICOM images, and it can deal with images, reports, and radiotherapy information. But note over here that it is single-threaded. Then there's DICOM Fauché, which is a collection of open source applications and utilities, again for healthcare and the enterprise space. It works in the Java environment. It's developed for JDK 1.6 and up. Then Matplotlib, that's familiar. So now we're coming into the Python space, right? That's useful for visualization. You might want to visualize the image. You might want to visualize certain plots or histograms or heat maps. So Matplotlib is very commonly used here. Why it's awesome is because it can be used in Python scripts, it can be used in notebooks, it could be used in web application servers. And then, of course, you have your machine learning libraries, unless you're implementing them from scratch. You might want to use something that provides you with the classifiers or regressors or failure analysis techniques, and also the matrix part that I mentioned, like eigen decomposition. So all of these are different tools and libraries. What we try to do is try to bring this all together into one library or one toolkit, which is what I'm going to introduce now. So this is the Spark TK library. It stands for Spark Toolkit. It's an open source library enhancing the Spark experience. So it leverages all the benefits that we can take from Spark, but also adds in third-party libraries to build this end-to-end solution. It has APIs for feature engineering, ETL, graph construction, machine learning, image processing, and scoring. So some stuff is what we've built over Spark. Some of them we've exposed Spark to be using for certain image processing solutions. It provides abstraction levels familiar to data scientists. So a frame is the data structure that we go with. Under the hood, it could be a data set, it could be an RDD, it could be a data frame. But a data scientist need not rack their head on this space and try to figure out which is best suited. So it removes the complexity of parallel processing. But if you're a Spark expert, like most of you over here probably are, you can still use the Spark APIs, which are exposed seamlessly. So depending on who you are, you can use this. And it's easy to build apps, and third-party tools and libraries can be integrated easily. So all of the tools that I mentioned previously, we're going to be talking about how we've used them in a distributed environment in Spark. And those are the two links. That's the GitHub link. Like I said, it's open source, so you're free to use it and contribute to the repository. And the second link at the bottom is the documentation link. Now I'd like to call upon Karthik to continue with the rest of this, and he's going to walk us through some of the Spark TK components and the demo.
Hello. Hey. Thanks, Anahita. Thanks for the good background on the DICOM. So now I'm going to talk first about myself. I'm Karthik. I work for the AI products group. And usually I'm involved in the framework development, like we develop the cloud tools for the deep learning frameworks. Okay, so let's talk about what is the Spark TK components and what all it contains. So basically the Spark TK, the building block is the frames, which are the scalable data frame representation. All it is a Python wrapper on top of the original native Spark. And it's more intuitive than the low-level HDFS file and the Spark RDD and data frame and data sets. And we have provided the different APIs to manipulate the data frames for the feature engineering, exploration, and we have written a well-optimized joins and the group bys and the aggregations. So you no need to handle all the complex operations as you do on the native Spark. We handle that for you and provide a Python layer on top of it. And for all our models, this frame is an input. And these are very easy to convert from the Spark TK frames, which are our representation to the native Spark data frames. And along with that, we have this graph API also, which we support, which gives us support for the graphics as original Spark provides. And even that has some good algorithms where you can use it. And here we provided some algorithms for the machine learning and the streaming. So like the time series analysis, recommender systems, topic modeling, clustering, classification, and regression. So here my main focus is on the image analytics, like what we did specifically for the DICOM image processing in the Spark TK. So as Anahita mentioned in the previous slides, there are different open source tools for accessing and processing the DICOM images, like say DICOM for Shea, which is the healthcare enterprise levelly used, but that is developed in Java, but that is not the distributed fashion. And we have the PyDICOM, which mostly the most Python data scientists know very well, but that at a time using the PyDICOM, you can load only the single image, and which is not that efficient for the distributed stuff. So what we did with our Spark TK library is just stitch all those open source tools and create a distributed and more scalable library on top of Spark. So here in this library, we well integrated the DICOM for Shea, so you can leverage the Java. And what we did is we took the Java and converted that to the Scala, and we did more distributed fashion. And also in this library, we provided machine learning for image and health records, like you are the new to the data science field and you don't know what algorithms to use and what hyperparameters to set. We have that hyperparameter selection and best algorithm selection, like just give this frame and take that, run that algorithm, so it will choose which model is best for your data, and it will give the set of hyperparameters for you. So, and let's go to the live demo. So in this demo, mainly focus on how we use our library. This is a Python notebook, which we created using the, so if you see here, this is the similar fashion if you're good at using the Python in the Jupyter. So this is how we import as a normal Python module from Spark TK and import. And here, the most important part I want to discuss is the Spark cluster conf. So if you're good at the Spark configuration, so you have to tell, so number of executors, driver memory, and the number of cores to set. So as long as you set the give the proper configuration, your the library scales very well. So here I'm running all these experiments on a single node where I have set the driver memory as per my cluster configuration, so you can change and customize as your needs. And if you see here, similar to the Spark context, here we have the TK context, which is on top of the Spark context. And here I'm running that in the yarn client mode, giving my external Spark cluster conf and providing the driver memory. And here I'm reading a very small data set. Okay, for you, let me rerun this entire notebook. So which right now I'm running on a very small data set of 100 images, which takes approximately 40 to 50 seconds to read that. And as Anahita mentioned in the previous slides, the DICOM is a combination of metadata and the pixel data. So when it is creating, this library will create a DICOM object with metadata frame and the pixel data frame. So you can do the pre-processing or ETL on top of the metadata. And suppose you have billions of images, you are interested only the subset of the images. You can do the pre-processing on the set of the DICOM metadata frame, and it will extract the subset of the images, and you can run all your image learning algorithms on top of it. So it did give me some output. Let me walk you through this entire thing. So here I'm reading the small 100 images. As I said, It's a DICOM object, and I'm loading the 100 images. You can see it's a count. The both data frame has 100 count. And this is a pixel data. The pixel data is nothing but it's a, here we are storing the pixel data as an ND array. It's just a dense matrix in the Scala. And here we support the pixel data as an ND array. So if you are good at using the ND array operations, you can perform all the operations here. Just import the NumPy and just do whatever the operations you want to perform and run all the external algorithms here. And so as I said here, each image is stored as a single record. And if you're interested to know what image this metadata looks like, so I just want to print that for you here. This might not make much sense to you now. So there is a lot of information which is not sensible to me, but if you are good at knowing what is DICOM, and if you are specifically interested in specific attributes in the DICOM, then just go and extract only those fields. Like in this entire information, I was interested only in the steady date. Like I need the timestamp patients in that range. So I just go and add that as a column to my data frame. So if you see, I'm just giving extract keywords. So it will go and look for that keyword steady date, and it will extract, and it will add that as a new column to your data frame. So this makes much easier your job. So if you're very specific about what fields do you want to work on, just extract that, add, and run the analysis. And here, for advanced the Python users, we provided the flexibility to write the custom UDFs also. Like you can write your own functions and more complex operations if you want to do on that metadata. So the metadata is just an XML file. If you are an expert in that XML query, you can do all that stuff there. So with this, I wrote my own custom UDF, and I'm adding the one more extra column, which is a SOP instance UID, which is unique for each DICOM image. And if you see, it added the extra column here and the timestamp. And in the same way, so once you extract all the columns and you want to just filter out the SOP instance UID, which are matching to some, here we didn't get a public data set, a very good data set, so we just grab something from the publicly available. If you have a real data set, you can run all on the top of it. And right now, I'm filtering out for only this specific SOP instance UID. I said it is unique for each image, so it will extract only the single image now. It will filter out, and now my metadata frame has a single image and its pixel information, so which is an ND array. So, and this is for the filtering, and now let's do a simple thing like just I want to reverse the operation, like drop the columns which match all the patterns. Like this is the same notebook, but only one functionality differing is I set all the configuration, but only at the end, I'm just dropping based on the same key. So like I would like to drop, filter all the columns and just drop which are matching to this specific pattern. So I'm just dropping, and now if you see the count is 99. So because it dropped that single record which is matching, and in the same way, so it gives you back all the information. And this is all the metadata information which is related to the devices, which is related to the patient, and you can run all the analysis on top of it. And why we are doing all this, because you cannot do all this operation on the image data. So doing the computation on the image data is very expensive. So before that, I want to do the pre-process and just clean and get only the subset of the images which are really useful for me and the data scientist. So now here goes something interesting. So I'm running the same analysis on the 100 data set. But here I'm concentrating on the pixel information. The pixel information is nothing but a matrix. Here we represent that as an ND array. So if you see here, now I have the 100 images of the pixel data. And here, if you see, as I said, we are storing that as a NumPy ND array. So you can do all the transformations you were doing with the NumPy, you can run on top of it. And we have provided, right now for the simplicity, we just ran the matrix SVD on top of that ND array, and we are adding some extra columns to run finally to run the matrix PCA, so the principal component analysis. So once you get to this stage, you got the feature extraction is done at this point. Now, till this point, we got what the data scientists need. Now the data scientist has to decide which algorithm is best to do all the predictions and all the analysis. So if you see, so this is the original, the brain image. If you are interested, we can forward this to later the session. So this is the open source publicly available data sets. So where you can go and grab the information about the patients, and these are the publicly available. So that is a sample usage of our library. Now, let me switch back. Yeah. Right now, we spoke about all the machine learning stuff. Now, there is a big boom on the deep learning. So what we can do in a very simple way is, so we wrote a Spark TensorFlow connector, which has been accepted by the TensorFlow ecosystem. So the main use of this is you can convert the Spark data frame as a TF records, and you can import the TF records as a Spark data frame. And if you are really interested in this, so here is the TensorFlow ecosystem, so where our Spark TensorFlow connector is available. So this is open sourced. You can just go and grab. You can run all that. So if you see, here is a sample example also how we are converting the Spark data frame to the TF record and how we are loading back the TF record. And finally, I would like to talk about the performance. So how well our library is scaling. So here, if you see, we didn't get much data. So we did run this analysis on 32 GB of data on a single node. So as you see, the processing time increases with the data. And we kept the number of partitions as 1,000. And the good thing we noted here is the number of partitions versus time. Like the number of partitions, the 675 is performing very well. Even if you increase the partitions, it of course degrades the performance. So it's good to maintain that. And this, all the performance numbers are specific to the cluster configuration, which I have talked about earlier. So that might differ if you run on a different configuration. And here the number of executors, as you see, as I increase the number of executors, the time gradually decreases. So it indicates the library is scaling very well. And here, the number of executor cores, we see that setting the 3 is giving you a very good performance. Yeah, and if you are interested in using the Spark TK, right now we are not actively maintaining this. So if you are interested, feel free to just go and clone and customize as your needs. Thank you.
Hello. Awesome. Thank you. And if you guys have any questions for our speakers, feel free to stand up and come ask them at one of the 2 standing microphones here in the auditorium.
Thanks for the talk. It was great. My question is if you also have done any work with like the Nifty format, or if you've converted it, because I'm working with DICOM imaging and sometimes I work with Nifty, and so I'm just curious to see if you're working with other image data formats also.
Hello?
Hello. Yeah. Right now we are supporting only the DICOM, and that too the uncompressed DICOM images. Yeah, there is.
But it's going to be fairly straightforward that if you can represent the image internally as a matrix, this can be scaled to any kind of image representation.
Thank you. You said you store all the pixel data as NumPy ND arrays. And so if you're storing these as Python objects, have you run into pain with like the huge serialization you hit as you go back from the JVM? Or is this manageable because it gives you the full power of NumPy?
Yeah, exactly. That's a great question. So we really paying for the serialization stuff because basically we are representing at the back end as a dense matrix. So yeah, we have to pay because on the Python, in the distributed fashion, if you want to represent, then you have to pay for the serialization. So to represent that as a NumPy array, yes. That serialization does have an effect, but not compared to the standalone which we have. And we have the Scala IPS, which is a dense matrix. So if you worry about that serialization, you can just go and invoke the Scala IPS instead of the Python. So you can get rid of that serialization problem.
Awesome. Thank you. Let's give the speakers a round of applause. Thank you.